One of the things that's very valuable in quantum computing and in science in general is the ability to write out a little bit of software and then never have to look at that problem again. For example, you can look at condensed matter physicists who like to diagonalize large matrices, and they don't rewrite their diagonalization routines from scratch every time, unless maybe they're going for an educational exercise or something. In a more professional context or in research, they'll use some prepackaged software in order to make their lives easier. This is also the case in quantum computing, where there are a lot of pre-compiled libraries that you can gain access to. And really, the number and efficacy of these libraries has been exploding recently. Let's take a look at a few of them. Wikipedia has a nice list of these under the quantum programming page, where they assemble a large series of these algorithms, libraries, toolkits, and indeed a lot of domain-specific and specialized languages that you can use to study quantum computing. There's Project Q, which is from Zurich and/or Microsoft, Qiskit from IBM, Forest from Rigetti, and the list goes on. It's mostly language-focused. If you wanted a specific library that does one thing and does it well, there are other places that you can go look. Like, for example, there's the venerable Quantiki, which is the quantum information wiki that's been around for a while. And if you'd like to find a job in quantum information or find out when the next conference is, Quantiki is a great place to look. But they also have a list of quantum computation simulators. And there are simulators broken down by language. So here we can see that there are some from C and C++. There's quite a few, including the QX simulator, which is developed at Delft. And if we scroll down, we can find that there's some more exotic languages like Camel, OCaml, Coq, F#. Let's see if there's anything special in the list. There are a few in Julia, so if you're more accustomed to Julia, if you've been working in JuliaBox in the quantum cryptography MOOC, which is also developed around here, then you might want to take a look at quantumoptics.jl, which is a more hardware-oriented library, or QuantumWalk, which is nice for studying fundamental quantum information processes. And there are many more of these libraries. There's a third big list that I found last week after I contacted the HiveMind on Twitter to let me know where all of these big lists are stored. And it's from Mark Fingerhuth. Apologies if I've pronounced your name wrong. And these libraries are divided by categories. So they have full stack libraries, simulators, libraries to do quantum annealing, but also libraries to do what's called experimental quantum computing, which is mostly, domain-specific languages, and something called generic lab tools. I'd like to conclude by calling your attention to one of the most well-developed libraries in quantum computing, which is QTIP, which a lot of researchers already have installed. So if I open up IPython here, and I wait, of course, for IPython to get started, then I can import everything from QTIP. And output some of the simple quantum objects that QTIP has ready for you in memory. So for example, the Pauli X matrix is stored here as a quantum object, which is a custom data type that includes metadata such as the dimensions of the object, the shape of the object, its type, whether it's a state or an operator, for instance, which can be difficult to track if you're using matrices, whether it's supposed to be Hermitian, so that you can check and make sure that there are no errors in your code, making something that's supposed to be Hermitian non-Hermitian, and then the matrix itself.
What?